So welcome back to part 2 of our section. So now I guess something has struck me with what Angela has actually mentioned, because what happens actually in the x-axis, what happens in the x-axis is that tension 1 x plus tension 2 in the x-axis. Of course, we know that in the x-axis they will be equal to 0. So meaning tension 1 x will be equal to tension 2 x, but this one have a negative. So it will be that in the x-axis we'll have the two tensions, the vector of the vector component in the in the x-axis for the two tensions will be equal to 0. So, but the vector component in the y-axis will be equal to y, and then when you do y squared, and then you do its square root, will be equal to w. So yeah, I guess it's also possible for the tutor to miss the point in the first instance. So indeed, what we are saying is that it's true actually that question C is correct. So for our friends who I marked wrong for part C, where I marked you guys wrong, I guess we'll make that correction. We are saying part C is the answer for F is C. Is that okay?
Yes, sir.
Yes, sir.
Okay. So yeah, you forgive me for that part. It's possible also because the tutor is a human being, obviously, he can have an overlap. But let's continue and see more questions and see how we can find them. So let us have Angela to help us read part G, question G.
A 500-gram ball moves in a circle 40 centimeters in radius at a speed of 4.0 meters per second. Its centripetal acceleration is?
Okay, you can even go ahead and help us with the answer and how you go about it.
All right. A, 80 meters per second. B, 40 meters per second. C, 20 meters per second. And D, 10 meters per second.
Okay, so we are saying that you can go ahead and even help us with the answer.
Oh, okay.
Mm-hmm.
What I found here, if I'm not mistaken, I think I found 40 meters per second. And how I did it myself was centripetal acceleration is equal to the speed, the V squared divided by R. I don't know if I went wrong with the formula or what, but that's what I did. And I got 40. And I got it wrong.
Okay, so V squared divided by R, right? Okay.
Yes.
So now, this is 4 meters per second and this is 4 centimeter. Okay, awesome. Yeah, indeed, of course, when you do 4 squared over 0 0.4, you will get 40. Okay, so awesome. Yeah, I think indeed this was supposed to be the answer. Yeah, I think I also had an overlaps on this one. So yeah, this is the answer, and this is how you go about with centripetal acceleration. So, yeah, is everyone clear on part G, how to find the centripetal acceleration?
Yes.
Okay, okay. What are the others? How the others who are quiet? Are they okay? Florence, Chipo.
Yes, sir.
Yes, sir.
Okay.
Awesome. So let's not be quiet, or else I'll assume the other guys are not okay with the answering. So, yeah. So who is reading next? Who is reading next? Let us have.
Me.
Okay, me. Is that Precious? Yes, Precious. You are the one. You said you want to read.
No.
Come on.
But I can read.
Yes. Mhm.
The question is, the total angular momentum of a system of particles A may or may not change under the influence of a net external torque depending on the direction of the torque. B changes when a net force acts on the system. C remains constant under all circumstances. D changes when a net torque acts on the system.
Awesome. Give us even the answer.
I think the answer is C, which is saying remains constant under. Sorry, no.
You are saying the answer is C?
I think the answer is C.
Awesome. Wonderful. Anybody also before we try and discuss this question? Anyone else as well? Angela, do you have any contribution there? Which one do you think is the answer?
Me, I think it's D. Changes when a net torque acts on the system.
Okay. Angela said changes when a net torque acts on a system. Anybody else who has an otherwise question answer? Anyone else to give us their thought? Okay, so quickly, let's see how, which one is the answer. So how does angular momentum change? So we say that how angular momentum changes is, so they are saying that the total angular momentum of a particle, what will happen is how it changes is like this. If the system is isolated, it's possible that it won't change. But if the system is tempered with, so it changes by angular momentum, we know that it is moment of inertia times angular speed final minus moment of inertia multiplied by angular speed initial. So how it changes over some period of time is when a torque is acted upon it. So when a net torque is acted upon it, mind you, it's not torque, it's torque. All right, torque. So that because you guys are students, but the next day you'll be professionals working in industries. You may be engineers working in the industry, and then sometimes it matters also that you get to know the correct pronunciation of some of these words. So this word is not torque, it is torque. So sometimes you might be an engineer talking about a particular motor, and you are giving the speed, and then you say the torque of this motor is this. So people may not get you clearly, even when you mean the actual word. So the pronunciation for this is torque, just like the way you say talk, talking, talk. So, but it's pronounced as talk. So I'm sure you can't fail to say talk. So this is not for me to undermine your mother tongue. No, everyone has their own pronunciation depending upon their mother tongue. But also, it's also important when, as an engineer or as a scientist, that when you go in a particular field and maybe you are talking about something, you mention it correctly so that the people can understand what you are talking about. So I just hope you can learn from it from today that this word is pronounced as talk. Yeah. Awesome. So the net torque is what changes for us to come from a certain angular speed to another angular speed, or from one angular speed to another angular speed. Over some period of time, we have to apply a net torque. That is how come where we changes. That's how come this is our correct answer. Changes when a net torque. Oh no, this is net force. Where is it? Where is our net torque? Changes when a net, yeah, D is our answer. Is our answer. Awesome. So let's quickly go to I. Are we okay on why H answer is D?
Yes, sir.
The others who are silent? Or what are we saying?
Yes, we agree.
So you should not be silent, you people. Awesome. So the moment someone else is reading for us this question, who I guess Florence can help us read this question.
It reads, the moment of inertia of a body comes into play, A, in linear motion along a curved path only, B, in straight line motion only, C, in rotational motion only, D, all of the above.
Awesome. So you are even telling us the answer to that.
I think it's C.
In rotational motion only. Okay, what do the others think? What does?
I think the same.
Angela, you are saying you think the answer is C?
Yes.
Okay, so anyone else to concur or to say otherwise?
I think it's G.
All the above. Awesome. So I guess with the inputs that have been given by the word moment of inertia, all right, how do we even define moment of inertia? Moment of inertia is a summation of all masses and radius squared, right? So whenever we talk about radius, what comes into play? We talk about something circle, all right? Only a circle can have a radius. So if we have a ball like that, if you throw it in the air and it's not rotating, its moment of inertia will not be considered. If you are computing its kinetic energy, you will not consider its moment of inertia. So it will not come to play because it's not rotating. But if you throw a ball and it's rotating like that about its surface and given its radius, what will happen is that since it is rotating, that is only when its moment of inertia will come to play. So its moment of inertia will come to play when it starts rotating about a particular radius. All right. So its moment of inertia, we have already described that it is mr squared. All right. Mr squared is a summation of all the masses so all the masses that are in this particular ball, when we sum them and we even sum at what distance they are, we'll get its moment of inertia. And when they are rotating now, all right, that's when now we can have our moment of inertia being considered. So let us get it from today that you can't have moment of, when you are doing, when you are solving motion in a straight line, you will not have to put moment of inertia in consideration. When you are dealing with a curved path, you may not need to deal with the moment of inertia, even if radius is concerned, but when you're finding centripetal forces, you don't usually deal with moment of inertia. All the above can't certainly be correct because we see that here moment of inertia doesn't come to play, and even here it's questionable. So here there's actually a question mark. But so therefore, especially since we know that in a straight line there's no moment of inertia coming into play, but there's inertia. If they just said inertia can be in all the cases, because even in moving in a straight line, inertia is that resistance to change of motion. But when they say moment of inertia, they already mean force or torque, all right? Force times that radius. So moment of inertia already talks about a radius, and a rotating object will only take place in rotational motion. So yeah, there we have it. Our answer is supposed to be supposed to be C. Are we okay? Precious?
Yes.
Awesome. Are we okay, everyone? Is everyone fine?
Me, I'm fine.
Yes.
Yes.
Yeah, so let us be responding so that we move quickly. Mr. Gilbert, you are reading the next question. J. I'm sure which is the last question.
I never wanted to read this because I don't want to attempt it. I failed. Let me go. An astronaut is weightless in a spacecraft. A, in all orbits. B, in certain orbits only. C, as it takes off from the Earth. D, only when the escape speed is exceeded.
Awesome. So what is your thought? What do you think will happen?
I answered in certain orbits only. I was marked wrong. But now maybe I would guess D, only when the escape speed is exceeded.
What do you understand by the term escape speed?
Actually, the speed that a spacecraft must reach for it to, as it escapes the Earth, for it to reach space without returning to the Earth. I think that way.
Awesome. I think that is the escape speed, and it's not the correct answer. Oh, in fact, I shouldn't have mentioned it. But okay, of course, it's not the correct answer here. Actually, when you exceed that escape speed, if you go to higher speeds, do you know what will happen?
No.
At the moment when you be accelerating, all right, trying to accelerate so that you reach this escape speed and you accelerate, do you know what will happen? You will feel as if 100 people are sitting on top of you. So you won't feel weightless. You will feel so heavy Sometimes you may feel double your own weight. Sometimes you may feel 5 times your own weight. Sometimes, depending on the acceleration that the escape speed is taking place. So what will happen is escape speed only gives us the amount of thrust where when we escape Earth, we shouldn't come back to it again. So that is not the answer. That is not what will keep you weightless. Anyone else to attempt? So there are only 2 questions. Mr. Gilbert got this one wrong. So there are only this one and this one. So among the 2 options, we can't know. This is now like tossing a coin. So which one do you think is correct? Madam Angela, what do you think is correct, the correct answer there? The only person who got it correct, by the way, is Chipo. Everyone got it wrong. But let's see now if we can change our minds. Oh, Madam Angela. Madam Angela, are you there? Could you help us with the answer? Part J. Okay, seems Angela is not with us.
Yeah, I'm back. I was disconnected.
Okay, so what's the answer for J?
J, what I put was like I put, I considered my answer to be D, but it was wrong. So anyway, I don't know what's the answer now. Okay, the I think the keyword there is weightless. I don't know how I do weightless myself. I think that's why I got the question wrong.
You don't know what weightless is?
No, I know, but I don't know. Anyway, this question is just somehow tricky.
Awesome, awesome. Some of you guys, I'm sure some of you guys who have had the privilege to go in an elevator, all right? You will discover that in the initial speed, when the elevator is just starting, going down, you get a sensation at that small point. Some of you guys even feel like, hey, you get that sensation when the elevator is just starting to go down. Do you get that sensation?
Yes.
It is a glimpse of weightlessness. If for example, the elevator cable was to snap, you feel very weightless. You feel like you don't even have any mass in your body. You will feel weightless. That is the same sensation which you get when you're falling. When you're falling from a very tall building, at that point you just feel like you're just a feather in the air. If you're falling, actually you can manage, even Precious can manage to do 10 push-ups when she's falling, because she won't feel any weight. But in the actual life, she can't even manage to do 1 push-up. But anyway, so what happens?
I can.
Yeah. So what happens is weightless happens when you are falling at the acceleration due to gravity. When you are falling at G, or when your acceleration is G towards the Earth, you get to fall. When your acceleration is G towards the Earth, that is when you can feel weightless. So now, which one among these questions gives us a good description? So what happens to astronauts? What they do is, so this is the Earth, right? This is the Earth. What they do is with a spacecraft, they will take off like that. They will take off at that angle, so that when they reach at a certain orbit, any orbit, it can even be an orbit which is just above your head. But what happens is that they must accelerate with an angular velocity of 9 meters per second squared, such that when the Earth is tilting, all right, the Earth is rotating this way, then they must be rotating this way, such that the acceleration due to gravity will be acting to pull them towards the Earth. All right. So, for example, if acceleration due to gravity is acting to pull you towards Lusaka, but since the Earth is rotating, by the time you'll be trying to reach Lusaka, Lusaka would have already moved to that point. It tries to push you again towards another point. That point moves again. That point moves again. So you will continue being suspended in the air, because even if you are trying to fall, the earth is moving. You are moving with a constant speed around the earth like this. The earth is trying to move you to itself, but you are keeping on rotating. So you'll be rotating with an angular velocity or an angular acceleration, so to say, of about 9.8 meters per second squared. More like the centripetal acceleration. All right. You know that centripetal acceleration is due to a curved path. All right. So if you are moving around the earth, all right, the centripetal acceleration will be trying to take you this way, while the gravity is trying to take you this way. So now if you are accelerating with a centripetal acceleration, and you know that centripetal acceleration is v squared over r. So this r, okay, I've seen your hand, Angela, just a moment. So this r can be any radius from the center of the earth, as long as you keep a certain velocity, all right, such that when you compute the radius, for example, if your radius is 5 meters per second, if your radius is 5 meters, what will be your velocity such that you reach a centripetal acceleration which is equal to 9.8? All right. So you would see that you would need to increase your velocity so that you keep up with the acceleration being equal to 9.8 meters per second, so that you do what? You maintain your orbit. And as you be moving around, do you know what you feel? You feel like you don't have weight. Even if you are moving on top of my head, the height of my head, but if you keep your centripetal acceleration equal to 9.8 meters per second, if you keep this value A, you'll feel weightless. All right. So what I'm saying, friends, is that at any orbit, you can experience weightlessness. The reason why these astronauts who are the satellites which are up there in the sky or just outside the Earth atmosphere, the reason why if you go there, you feel weightless is because that satellite has been thrown or has been projected at a certain velocity, such that if you do that velocity divide by the radius from the center of the Earth to that point, that acceleration will give you equal to 9.8 meters per second. That is only when you can feel weightless. So you can feel weightless in all orbits. Yes, Madam Angela.
Okay, I just wanted to say thank you very much for me being with you people. It has been nice. I'm leaving now. I'm having a class of maths with Mr. Keith. So I just want to get the answers from the question I went wrong with. So I think I'm leaving you people now. Thank you very much.
Good, good. You are always welcome even next time. And if you wish to be a permanent member of us, you can always say so. And yeah. Otherwise, thank you for having you. Okay. So question J, answer is A. Are we okay with the explanation why answer is A?
Yes, sir.
Yes, sir.
Precious?
Yes, sir.
So Precious is still saying that she can manage to do one push-up even on Earth without rotating at this speed, at this orbit, which will make you weightlessness. We'll try and do that experiment one day. But otherwise for tonight, this was the multiple choice questions. Of course, there are two questions that I realized that these questions I had an overlap. One question is this one. In fact, another one is this one. Some of you guys who I marked this one wrong, this one was supposed to be correct. And then the other one is that one. So some of you guys could have gotten better marks, close to 90% or so, but I had an overlaps on some of these two questions or three questions or so. But anyway, the idea for this is just to see you guys, since you always have your quizzes in multiple choice part, I just wanted to get a feel with you of how we can actually discuss some multiple choice questions and see how you guys can be able to have an enlightened mind, even when you are going in a quiz where there are multiple choice questions. At least you have that analytical mind of being able to figure out the right answer. So I guess that's all for tonight. Are we okay?
Sir.
Yes.
Yeah, it seems the Friday we are having a quiz on mechanical properties of matter. I think that's the topic.
Okay.
So I suggest we can, the next lesson we have, we do the same on the same.
Okay. Like I said earlier on, if you have some past paper, or me, I don't usually have past papers in NS because obviously I'm not in NS. But if you have some past papers, you can bring them in so that we can discuss them. But of course, I'll try and prepare something for our lesson. So, but I also wanted to quickly talk about this question, which most of you guys got wrong. This question, just quickly, where you have, they are saying a person can throw a ball to a maximum horizontal range. So when they use the word maximum, so the time when we have a maximum range, all right, the time when we have a maximum range is when the angle at which you throw that velocity, that object is 45. So 45 is when we have a body, or when we throw it. For us to have maximum horizontal range, we already know that the angle which they used was 45. And some of you guys were getting this range and solving it in the y-axis. This range is always, whenever we hear range, we talk about the x-axis. So what happens is that if you have your angle, what now you'll be looking for is the time. How long does it go high? You know that in the y-axis and in the x-axis, and in the x-axis, this is y, and in the x-axis, one thing that relates the two is time. So you discover that once you write out your equation of range in the y-axis, which is equals to the velocity in the x-axis, which is v cos 45 multiplied by your time. You can even make time the subject of the formula so that you replace the value in the y-axis solution. Mr. Gilbert tried to use that formula well, but the problem is he replaced, when he was replacing in the y-axis, all right? So in the y-axis, in the first instance, solve it when the displacement is 0. So solve it when it goes up and comes down, so that it reduces the number of unknowns. So you solve in the y-axis when the displacement is 0, and then where there will be time, you make time the subject of the formula in this question and call it equation 1. Wherever there will be time, you replace with what you make time to the subject of the formula. And then you discover that the only unknown will be v, and then you'll be able to solve your v. From after you have solved your v, you go back, you come back to this equation, you will solve for time. After you have solved for time, you will get half of that time. Half of the time is what is required to reach us to the maximum height. All right. half of the time is what is required to reach us the maximum height. Then when you get half of that time, after I've found that half of that time, you go back now to the y-axis. Now you write your equation now, y is equals to, you would have found your initial velocity, and then, you know, initial velocity, obviously you use cos 45, because what can give us maximum range is cos 45, and you have found your time, and then you even put the acceleration due to gravity, you'll be able to find your maximum height. So it was a bit tricky, but the thing is, it was not hard, it was not impossible to solve. None of you guys got it correct. So, but that is how you're supposed to go about it. Are we okay on that one?
Yes, sir.
Yes, sir.
Yes.
Awesome, awesome. So hopefully posting the video on YouTube so that our friends who have not had the opportunity to go through with us can also go through it in the night. But I marked your test, like I said, you guys have potential. Since there were some of the questions, the way you are solving them was beautiful. That is the way to go. But some of you guys didn't finish solving. I have told you that you can finish solving so that I can mark you together with the other questions. But even the other questions are not very wrong. And then again, another thing that I would just like to say about question 2A is that when they say draw, sketch the diagram, don't draw it like this. For example, you say, you draw it like that. For example, here where they say runs 145 meters, 20 degrees east of west, then you draw it like that. Maybe you draw it 20 degrees east of north is this angle. You draw it like that, and then you get the other one, which is saying 205 south of east. Then you draw it down south of east, and then you say 35 here. You don't draw it like that. You connect them. How you connect them is like this. You draw your diagram like that. So when they say 145 at an angle of 20 degrees north, east of north, you draw it, the 20 degrees there, you put an arrow like that. When they say again that 105 at an angle of 35 degrees south of east, south of west, from there, that's where you connect it. You connect it like that again. All right. You don't start from here again. You connect it from the top there. Here you can just draw a dotted line and show that my angle here is 35. All right. All right. But then the resultant now force will be, the resultant direction now will be there. All right. So obviously you may even get that angle to be the angle with which you be getting it with respect to. So, but that's how to actually, you have to connect them from where one ends, that's where you connect the other one. So otherwise, that is the lesson for today. Wonderful to have you guys and revise these questions with you. If you have any queries, you can still inquire with me in my inbox. Otherwise, this is good night. Have a blessed evening.
Thanks, sir. Good night too.
Awesome. Yeah.